Welcome back to the chemical bonding chapter. So in the previous video we have seen the bond length, the bond character. Among them the bond length we have seen. Now let us go for the second one, that is bond energy. Bond energy. It is the energy required to break 1 mole of a similar kind of bond between the two atoms. Suppose you consider this energy that is required, to break 1 mole of a similar kind of bond, between two atoms bound by a covalent bond. Suppose you consider this hydrogen atom which are bound by a covalent bond. Suppose you take this 1 mole of hydrogen molecule, so that the atoms that are produced are in the isolated gaseous state. So we can also include bounded by a covalent bond to convert them to a isolated gaseous atoms. So which gives rise to isolated gaseous atoms. Here you just remember the difference between the bond energy and ionization energy. Ionization energy is nothing but removal of the electron. But here the bond is broken so that both the atoms are produced in the isolated gaseous state. So whatever the energy that is required, it is named as the bond energy or bond dissociation energy. So there are so many factors which govern this bond energy. Factors governing bond energy, also called as the bond dissociation energy. The first one is the size of the atom. If the size of the atom is larger the size of atom, lesser is the energy, lesser is the bond energy or bond dissociation energy. So as the size of the atom goes on increasing, the bond length increases. As the bond length increases, the distance between the two atoms increases, or the nuclei of the two atoms increases, and hence energy required to break such a bond is lesser one. Suppose you consider the bond between the hydrogen atom and a halogen atom like iodine. Since iodine is larger in size as compared to hydrogen atom, the bond energy required to break this 1 mole of hydrogen iodide bonds is smaller as compared to the energy required to break the hydrogen bromine bond. Similarly, this in turn is less as compared to this hydrogen and chlorine bond. Similarly, it is less as compared to the hydrogen and fluorine bond. That means among the hydrogen halides, more energy is required to break the bond between the hydrogen and fluorine atom, because fluorine atom is smaller in size as compared to the chlorine, bromine and iodine. So this is one character or a property that actually governs the bond energy, size of the atom. The second one is multiplicity of the bond. Multiplicity of the bond. Multiplicity of the bond is actually nothing but the number of bonds between the similar atoms. Suppose I take this carbon-carbon single bond, comparing to carbon-carbon double bond, comparing to carbon-carbon triple bond. When you consider this carbon-carbon single bond, it is larger in size as compared to double bond, as compared to triple bond. That's why the energy required to break the carbon-carbon single bond is lesser as compared to the double bond, as compared to the triple bond. And in case of the multiple bonds, The bond energy is actually taken as the average energy for breaking the two bonds. Suppose for a carbon-carbon double bond, when you break this first bond, let us say the energy required is Be1. For the second bond, let us say, which is actually more as compared to this Be1, it is Be2. So this bond dissociation energy or bond energy is taken as the sum of this Be1 plus Be2 divided by 2. For the oxygen atom, to break the two bonds, more energy is required, and first energy is lesser as compared to the second energy. So the average energy is taken as the bond dissociation energy in case of the multiple bonds. But still, the bond energy for the single bond is larger, smaller as compared to bond energy for the double bond. So this is about the multiplicity of the bond. The third one is the lone pair of electrons. Lone pair of electrons. Suppose there are lone pairs of the electrons on the atoms which are bound by a covalent bond. Then automatically there will be repulsion among the lone pair of electrons. Suppose you consider this nitrogen-nitrogen triple bond. We know that both the nitrogen atoms have got lone pair of electrons. Since this lone pair repulsion with the lone pair repulsion is more, automatically this bond becomes a little bit weak. But in case of this oxygen-oxygen double bond, there are two lone pairs on the oxygen atom, each oxygen atom. That's why there will be more repulsion in case of the oxygen-oxygen bond. That's why the energy required for this one is lesser as compared to that for the nitrogen. So nitrogen-nitrogen bond dissociation requires more energy as compared to oxygen-oxygen bond dissociation. Higher the number of lone pairs. So we can write this as higher the number of lone pairs, higher is repulsion, and smaller is bond energy. Smaller is bond dissociation energy. So these are the three factors which govern the bond energy. The next property that we consider is bond angle. Bond angle. Suppose you consider two bonds for the central atom which are bound by a covalent bond. Two other atoms bounded to the central atom by means of a covalent bond. Then there will be some angle between the two bonds. Such an angle is named as the bond angle. Suppose I consider this hydrogen-oxygen bond. Hydrogen-oxygen-hydrogen bond. This is not actually linear. So we observe in the future topics we will study the bond angle, that is HOH. So this angle between the two bonds are which is present between the orbitals containing the bonded pairs. That is actually named as the bond angle. There will be some empty orbitals also containing the lone pair, but we consider the bond angle between the two bond pairs. So such an angle is named as the bond angle. So these are the other two bond characteristics. One is the bond energy, the other one is bond angle. This bond angle is actually useful for the determination of the structure of the atom, structure of the molecule. Energy required to break 1 mole of a similar kind of bond between two atoms bounded by a covalent bond to give rise to isolated gaseous atoms. It is called as the bond energy. So for this bond energy, there are so many factors. One is size of the atom, larger the size, lesser is the bond energy. Multiplicity, larger the number of the bonds, higher is the energy. Lone pair of electrons, larger the number of lone pairs, lesser is the bond energy. The angle between the two bond pairs or orbitals containing the bond pairs is named as the bond angle. This is useful in determining the structure of the molecule or shape of the molecule. The next one is characteristics of the covalent bond. Characteristics of covalent compounds. Characteristics of covalent compounds. Since ionic bond is a stronger bond as compared to covalent bond, ionic compounds have got high melting and boiling points, but covalent compounds have got low melting point and boiling point. Low melting point and boiling point. The second one is, these are the either low melting solids or liquids or gases. So they may be either solids or liquids or gases. In case of the solids, they have got very low melting points. Then the third characteristic is, they do not conduct electricity. Either in, that's all. The next one is, are insoluble in polar solvents. Insoluble in polar solvents, but soluble in non-polar solvents. For example, if you take the carbon dioxide is a covalent molecule, or methane is a covalent molecule. It is more soluble in the non-polar solvents like benzene, toluene, etc., but insoluble in the water. So, as I told you, in the case of the ionic compounds, like dissolves like. This is covalent molecule, that's why it is soluble in the non-polar solvent. Then the bonds are directional. Then which gives rise to the specific shapes to the molecules. Reactions are very slow. So these are some characteristic properties of the covalent compounds. General characteristic properties of the covalent compounds. They are low melting solids, liquids or gases. They have a very low melting point and boiling point. They do not conduct electricity, and they are insoluble in polar solvents but soluble in non-polar solvents. Bonds are directional. So in case of the ionic compounds, we don't write any bond between, or we don't write the directions. But in case of the covalent molecules, we write the directions between the two atoms. That is, suppose you take this water molecule, it is a covalent molecule. We write the bond. This bond is directional. That's why these bonds are considered as the directional, which gives the definite shapes to the molecules. And the reactions are very, very slow as compared to the ionic compounds. So the same characteristics we can use to distinguish between the covalent molecules and the ionic compounds. So ionic compounds are high melting and boiling points. They are solids, usually solids, have got definite shapes. And even in the solid state also, they contain some ions. And they conduct electricity either in the molten state or in the aqueous medium. They are soluble in polar solvents but insoluble in the non-polar solvents. Then in case of the ionic compounds, the bonds are non-directional. In case of the ionic compounds, reactions are very, very fast. So these are some distinctions between the ionic compounds and the covalent compounds. So in the next video, we will go for the formal charge on the atoms in a molecule or ion. So though there may be no charge on the each atom, for some purpose we require the assignment of the charges on the atoms. So that is called as the formal charge. That formal charge we will see in the next video. Thank you.